Okay. All right. So let's get started. First of all, the people who joined online now, thank you very much for your patience. I will do my best to admit new people who are joining online and monitoring the chat as well for any questions. So hopefully I'll be able to admit future joiners much more quickly. So let's get started with hardware. So my name is Andre, and I'm a research scientist at Waabi, and I work on localization and sensor simulation primarily. And today, for this session, I'll be covering hardware and sensor configurations for autonomous driving. Okay. So we'll be covering the major kinds of sensors that are typically used in autonomous driving in this session. And we will go over the inner workings of different kinds of sensors that are used in autonomous driving and go through their pros and cons. We'll give a brief overview also of the kinds of computers that we typically want to look at when we're running these kinds of autonomous vehicles. And then we will also show how all these pieces actually come together in order to build a robotic system. So I will talk about a lot of sensors like LiDARs and cameras in this talk, but deep dives within an individual sensors are outside the scope of this talk. So I'll only cover kind of the high-level basics and the high-level pros and cons, but there are a lot of references, especially at the end of the deck, to other resources where folks who are interested in learning more can dive deep into specific sensors for hours. Okay, so let's begin with sensing. We begin by first thinking a bit about what aspects are desirable in a platform. So here, robustness is paramount, right? We have a piece of hardware, a robot that will be out on the road, exposed to all sorts of vibration, dust, potholes, weather conditions, and so on for many hours on end, while being responsible for a multi-ton vehicle, potentially at very high speeds. So safety here is critical. And naturally, we want sensors that are individually resilient, but also a platform that has enough redundancies in case of potential failures, while also being able to operate in various kinds of weather conditions and various kinds of lighting conditions and so on. We want the sensors to provide information about the environment itself, as well as about our actions upon that environment and our state. So we want to be able to sense the geometry as well as the appearance of the environment. We want to have information about the road configuration, as well as ways of determining very precisely where in the environment we are and how the vehicle is actually behaving. So both kinematics and dynamics. So we will start briefly by talking about GNSS and other sensors that are typically used in state estimation. So these kinds of proprioceptive sensors like wheel encoders and so on. And a lot of these sensors have actually been very common in vehicles for a very long time. So things like wheel speed sensors, and even GPS have been pretty much omnipresent in vehicles for the past couple of decades. And of course, these sensors are used in autonomous driving as well. So we have things like wheel encoders and inertial measurement units that are typically fused with information from the Global Navigation Satellite System, or GNSS, in order to produce course estimates of the vehicle position. Okay, so let's have a closer look at these kinds of sensors now. So we begin by having a look at the Global Navigation Satellite System, or GNSS, of which the United States GPS is probably the most famous implementation. And these are essentially beacon-based global localization systems, which leverage time delay measurements to multiple satellites in order to infer your actual receiver location. And for consumers with no costs, other than the receiver itself, consumer-grade GNSS is actually highly inexpensive. And at the same time, with most receivers being able to connect to multiple constellations, so it's very common to have your receiver being able to connect not just to American GPS, but also to Galileo, GLONASS, and so on. You are basically guaranteed to be able to see a lot of satellites pretty much anywhere on Earth that you have a view of the sky. But of course, GNSS is not without its limitations. So using GNSS systems alone without additional corrections or anything like this can typically not give you the centimeter level accuracy that you want for self-autonomous driving if you're leveraging any kinds of HD maps. And while real-time kinematic or RTK systems leveraging differential GNSS can reach higher precision, they are substantially more expensive typically, both in the receiver and in the subscriptions. And they might require the availability of base stations near where you're driving. And furthermore, satellite readings themselves can be unreliable or completely unavailable, as you probably know, in places like urban canyons and other areas, underground parking lots, long tunnels, and so on. And so in those areas, you cannot easily compensate without additional sensors. So in these cases, you probably need to do some sort of map-based localization or visual odometry or something like that. So real-time kinematic systems, or RTK systems, are kind of the next tier of satellite-based processing. And while they require more sophisticated technology, as well as, like I mentioned, the availability of base stations, they can deliver basically centimeter-level accuracy for autonomous robots in a very wide range of environments. So the idea behind these real-time kinematic systems is that they use two major principles in order to improve the positioning quality. So first, they rely on differential GNSS, and they use carrier phase measurements to enhance precision. And differential GNSS essentially relies on the presence of a base station to be near where you're driving, and something like within 75 or 50 kilometers. And this allows your system to receive corrections for things that are happening in real time, like various atmospheric delays that are causing issues with the signal, and account for these to dramatically improve the accuracy of the pseudo ranges. Okay, and how do carrier phase measurements help then? Well, regular GPS typically aligns a binary high-level pattern called the pseudo-random noise between what it's getting from the satellite and what it's generating internally. And by aligning these patterns, it can basically figure out how far the satellite is and establish a pseudo range. And this is very robust, actually, but can have some limitations in accuracy. So as we can see in the diagram, you have a limitation of roughly 60 centimeters in this setting based on the band you're operating in, which is typically the so-called L band of the radio spectrum. But if we go one step deeper here and we actually look at the carrier wave for the pseudo-random noise, we can actually estimate its phase to further refine this measurement kind of in a coarse-to-fine manner and allow us to basically improve the estimation of our pseudo range much, much better in order to a theoretical lower bound of about 1 millimeter, which is pretty much more than you can ever need. So to summarize, these RTK systems are much more accurate than GNSS alone and are widely available around the world. But they require more expensive equipment typically, as well as the presence of and often somewhat expensive subscription to base station corrections. And of course, on its own, RTK is still not magic. So if you cannot see the satellites at all, or the measurements are extremely noisy, you'll still not be able to localize. Another family of sensors are inertial measurement units, and these track the vehicle's linear acceleration as well as their angular rate. And they typically consist of two major components, which are some kind of accelerometer and some kind of gyroscope. And accelerometers are typically implemented as spring mass damper systems, and they're fabricated pretty easily as microelectromechanical systems or MEMS, which makes them very, very inexpensive in a lot of cases, as well as highly compact. So that's why these inertial measurement units are pretty much everywhere, even in your phone, and many robots just end up having even multiple of them. And on the gyroscope side, again, there's a huge body of physics that can be discussed to kind of categorize them in different ways. But typically in robotics, it's very common to have some sort of optical gyroscope. And again, you can check out the references at the end of the talk for more textbooks that actually give you more info if you want to dive deeper into the different kinds of families. And in terms of strength, like I mentioned, IMUs are highly inexpensive. They're available pretty much everywhere. And they often provide readings at really, really high frame rates. So typically hundreds, if not even thousands of hertz, which is great. And while tactical grade IMUs can have substantially small drift, like less than 1 degree per hour, consumer grade ones are a bit more sensitive and they drift a little bit more. So they are typically, you kind of have to use them in conjunction with some other systems. So, you typically use them in conjunction with visual information or LiDAR and visual or LiDAR inertial systems, or you fuse them with GNSS readings and feedback this information to keep the bias under control. Okay, so as initially introduced for perception, we want sensors that actually capture the state of the world around us, right? So one of the most common ways to do this in autonomous driving is, of course, LiDAR. You're probably familiar with this, and it's very, very widespread in autonomous driving. Radars are also quite similar to LiDARs in their inner workings, and they provide a very nice complementary setting. There are other sensors that are quite common in this as well, like ultrasonics, which provide range information very reliably at short range. Of course, there are things like cameras and microphones that can also be used for additional modalities. So let's dive a little bit deeper into each of these kinds of sensors. To begin with, radar is a sensor that has some similarities to LiDARs, for example, but instead of lasers, it uses radio waves. And the idea is you use some sort of antenna to emit low frequency waves and then capture their reflections. And by figuring out the angle and the time delta of this return, you can kind of figure out the 3D position of where the thing you hit was. And one extra benefit of radar over many other sensors is that by observing the change in frequency, so the change in frequency between the emitted and the received wave, can actually give you information about the radial velocity of the target, in addition, in accordance to the Doppler effect, in addition to just the range alone. So you're also basically able to modify the emitted wave to kind of toggle between sort of more spread or longer range. And this gives you basically a lot more flexibility into what you're actually perceiving with the radar. So you can actually dynamically adjust this. But of course, radar also has the ability to operate through more kinds of weather patterns than other kinds of sensors because of its operating principle. But of course, the fact that it can be robust to different kinds of weather interference also has the downside. It can also potentially miss smaller objects. So it is very important to use radar in conjunction with other sensors that have different strengths. And of course, last but not least, it has lower resolution than LiDAR. Typically, although imaging radars can be an exception to this. And then it's, of course, also sensitive to multiple reflection issues and other artifacts like ghosting. So you need to be able to account for those either in hardware or in software. The next family of sensors that we can talk about, of course, are the LiDARs themselves. So there are another sensors that is quite ubiquitous in autonomous driving, and they work essentially by shooting a laser beam, which is typically some sort of low power infrared down a predetermined angle, and measuring how long it takes for the return to come back. And this defines basically the range of that point, and combining the range with the angle gives you the 3D Cartesian coordinates. And they can employ anywhere from just one laser to along the zenith axis to a few hundred. And in self-driving, it's very common to see things like that have 64 or even 128 beams in this vertical axis. And typically when you do one sweep around the scene, you get between 80 and 150,000 points in your point cloud. So there's quite a lot of information to work with. And the strengths are, of course, that you end up producing direct 3D geometry that you no longer need to process to get the scene structure. And of course, they also don't really care about the lighting conditions in the environment because they emit their own infrared light. So they operate pretty much the same way, whether it's broad daylight outside or in the middle of the night. And by measuring the change in strength between the emitted and the returned photons, you actually can get a bit of information about the reflectance of the things you see in the environment, which can be very informative about the color or the material of the thing you're hitting. So this can be actually really, really effective at figuring out signs, lane markings, and other things that are pretty much omnipresent in environments where we want to drive. So it's kind of fortunate that a lot of these very reflective things that were designed to be reflective for humans are actually very reflective in infrared as well, and they show up on LiDARs. But in terms of limitation, of course, while costs have been going down, they're still typically quite high, especially compared to various consumer grade cameras. And at the same time, the resolution of LiDARs, even those with many beams, is still limited. So if you think about 128 beam LiDAR, the vertical resolution of your sweep will be 128, whereas an HD camera, the vertical resolution would be over 1,000 pixels. So there's still a bit of a raw resolution difference in that sense. And of course, you can be more sensitive to weather than other sensors, like, for example, the radar that we just talked about. And you might also be sensitive to things like mirroring artifacts. For example, if there's puddles, they might actually reflect the beam and cause some sort of ghost returns. And typically you are able to sort these out by either using various priors on the ground height or in software, but it is still something that is important to be aware of. But of course, these kinds of spinning LiDARs are not the only kind of LiDAR. So you also have various families of solid state LiDARs that are essentially cutting edge designs that are meant to reduce the number of moving parts and basically make them less expensive. Various kinds of solid state LiDARs are becoming more and more popular with all sorts of consumer electronics. So they're becoming common in things like some game controllers and, of course, many phones nowadays. And of course, they're much smaller and with fewer beams than these automotive grade ones, but they still provide a very rich information. So there's still a lot of subtypes of these so-called solid state or quasi-solid state LiDARs. So in this talk, we will go over some of the main categories. So one of the main designs are the so-called gated cameras, which essentially work by emitting an infrared pulse at a specific frequency and then making a sequence of gated captures of that image, each corresponding basically to a controlled round trip of the light in the environment. So in a sense, you are directly perceiving a kind of multi-plane image almost. And while this works quite well, of course, the issue now is that you have, instead of a continuous value for depth, you have kind of these depth bands, these discrete range bands. So it's a bit more coarse, but it still gives you a good sense of the structure of the scene. So these kinds of sensors, like we saw, they're more robust since they're going to be less affected by things like the vibration of the vehicle and other environmental factors. And because they have this instantaneous capture in a lot of these designs, you avoid a lot of the rolling shutter problems that you would encounter, for example, with a spinning LiDAR. And we touched a little bit on some of these cons when we were going over the design, but the idea is that the range of these kinds of sensors is a little bit more limited because you are kind of limited by the number of photodetector cells, and often because you need to cover the entire scene 360 around the vehicle. Sometimes you might need to add more physical sensors to a car rather than maybe a single top spinning LiDAR. So in this case, some of the costs might actually balance out, even though individual units are cheaper. So here's an example from one of the companies that provide something like this. So here you see that essentially when you project the LiDAR onto the camera image, you get pretty much perfect alignment all the time, because if both your camera and the LiDAR are global shutter and they are hardware synchronized, you don't need to worry about any rolling shutter effects, which is very beneficial. All right. Another design, which aims at more or less marrying the best of both mechanical and solid state LiDAR, uses MEMS, these micro electromechanical systems, to control a small mirror that basically directs the beam onto the desired angle as you're doing a scan of a scene. And in a sense, because you're still moving something, it's kind of a quasi solid state system, in the sense that there's still some sort of mechanical actuation, but the mechanical actuation is at the micro level. So it's much more compact in terms of the mechanical side of things, and the laser and the main optics themselves are static. So there's overall still much fewer moving parts compared to a regular spinning LiDAR. And an interesting application that something like this now is enabled is the fact that because you can control how you're steering this beam, you can actually do it in software and configure different scanning patterns for different applications. So for example, if you're doing highway driving, and you want to focus a lot on a long range along the road, you can kind of focus on scanning more directly in front of you to more easily detect maybe stopped objects or obstacles and so on. Of course, this comes with its own set of challenges, because you might be more sensitive to the amount of energy you're putting out because of this tiny mirror. So you need to do these trade-offs. Yet another family of LiDARs uses a somewhat different principle. So instead of current LiDARs that we've seen so far, which use basically pulsed amplitude modulated LiDAR laser, and they basically do time of flight measurements to figure out the range. Different approaches are more similar to radars, and they actually use continuous waves. So you have these kinds of LiDARs that use essentially frequency modulated laser. And then your range is no longer directly the time of flight, but it's measured as essentially a frequency shift between two coherent waves, right? You have the frequency shift between whatever you get back as well as your internal oscillator. And you can infer the range from this. And an interesting side effect of frequency modulation actually is the fact that you can simultaneously measure the radial distance as well as the velocity, again, because of the Doppler effect. So this has a bunch of benefits, but of course it comes with its own set of challenges, because now you want to estimate the position of the things in the scene. That's the main benefit of a LiDAR, and you want to get the velocity from this method. But both of these will affect the frequency of the returned wave. So you actually need to come up with strategies in hardware or in software to actually disentangle these effects. And the frequency comparison between the source and the reflective waves is also only possible if the waves stay coherent. So this potentially might also limit the range of the LiDARs as a function of the coherence length of these waves. So here's a quick demo of what this would look like from a manufacturer that does this kind of laser. So you can see that there on the top, you can actually directly perceive motion information in the laser. So this can act as a very, very strong prior to whatever perception system you have and make it more robust. Okay, so to talk a little bit more about LiDARs, in the past and even quite recently, LiDARs have kind of been considered as the most expensive sensor component that dominates the substantial part of the expenses of any sensor setup. But in the recent years, the cost dynamics surrounding these LiDARs have shifted quite a lot, and a lot of the prices are actually experiencing a steady decline. So as their popularity grows, LiDAR costs have started to become subject to economies of scale, and prices are slowly but steadily going down. So you can see some of these trends separated by the kind of LiDAR. And this is an analysis that was done quite recently by Bloomberg, where depending on the kind of sensor, prices are going down. But of course, typically simpler sensors are also able to cost less. So you can see that the Y scales are much smaller as you go towards the pure solid state LiDARs. So, something like 8 or 10 years ago, you might have been stuck with something like a Velodyne 64 being your only option for a high performance system, but now there's a lot more options in the field, and many spinning LiDARs end up, becoming much more affordable than that. And a lot of solid state LiDARs are commonly advertised as costing roughly $1,000 or even less. And some units are advertised for maybe $500 or even $100. And for reference, depending on the volume you're purchasing, if you want to be investing in high-end automotive cameras at relatively low volumes, you can easily exceed $500 per camera if you're buying really high quality optics, and you account for things like wiring, housing, power supplies, and so on. So the gap is definitely shrinking. And some examples include something like the Luminar Iris, which is advertised as around $500, and then even less expensive units like the Velobit from Velodyne have also been advertised as even as cheap as $100, for example, for these drone applications. Okay, so let's shift gears a little bit and talk about cameras, because cameras are, of course, yet another sensing modalities, and that we saw now that we saw the LiDARs. So cameras are very familiar to all of us, most likely because we've probably interacted with them for the past few years on a daily basis. So they have a lot of benefit. So they basically operate on the principle of a matrix of photoreceptive cells that filter out each specific color band. So you typically have this kind of grid of red, green, and blue filters, with typically a bias towards more green cells to mimic kind of human perception. And then you often in hardware extract the RGB color by interpolating the information from this grid. And of course, this red, green, green, blue pattern has been common for a very long time. Now, a lot of cameras have a lot of much more advanced patterns that optimize for different things. So of course, cameras have a lot of pros and a lot of cons. So by directly perceiving the color in the scene, you can directly infer the texture, the material of the scene, which is extremely informative for pretty much anything you want to do in the environment. And they're also quite inexpensive, providing high resolution data while also being vastly available, which also means that there's a lot of literature on how to actually effectively use their data. There's many, many decades of data on camera perception. They also provide pretty high frame rates, anywhere from 30 to 120, maybe 200 FPS, which can be very beneficial for high reaction times. And as long as you're getting high quality global shutter cameras, you typically have to worry about rolling shutter. You typically don't have to worry about rolling shutter at all, or it's much smaller of a problem compared to, for example, a spinning LiDAR. And of course, modifying lenses also gives you a lot of flexibility into the field of view, the range, and so on. But of course, there's still a lot of limitations because on their own, without, for example, multi-view systems or stereo, you don't have explicit depth information. You're also sensitive to the environment lighting conditions because fundamentally you're an ambient light sensor, right? And you are essentially reliant on external illumination to be available, which might not always hold in challenging environments. And of course, there's also the potential for artifacts. So there might be lens flare and distortion and stuff like this, which you always need to be able to account for, calibrate, and so on. And last, but definitely not least, event vision sensors, also known as neuromorphic cameras or dynamic vision sensors, are a much newer generation of sensing that kind of departs from the traditional family of frame by frame sensing by operating on the principle of asynchronous event-based processing. So instead of integrating data for each frame and then emitting a frame once at a time. Event cameras actually asynchronously fire off events on intensity changes in real time with extremely high fidelity and very, very, very low latency. So something like a microsecond of latency often. So in terms of strengths, these sensors typically have very, very high dynamic range. So they can operate, for example, as you're going in and out of tunnels with pretty much no problem. They have really high temporal resolution. Again, they amount to thousands of frames per second or more, which allows them to excel in scenarios where you have very, very high speed motion. And they consume actually very little power. So they're very beneficial for embedded systems and low power drones. And in terms of cons, much like classic cameras, they don't perceive the 3D information directly. So you would have to rely on stereo or multi-view systems, whatever, in order to get 3D information like that. And they're typically a little bit lower in spatial resolution compared to traditional cameras. And finally, they're also a little bit less standardized and less studied than other sensors, which might mean that there might be a bit more more software engineering and research necessary in order to integrate them into the autonomy system. But of course, as they're growing in popularity, this quickly shifted. So we can see a video of actually a GoPro video compared to an event camera's event stream on the bottom. So you can see that while it's very difficult to see things in the top image, pretty much everything that moves is extremely obvious on the bottom. And especially in the second part of the clip, you can see pedestrians extremely clearly when they're moving in front of the car in potentially dangerous situations, even though they might be very difficult to see in a camera image alone. Okay, so let's move on. All right, so we have our sensors now, and maybe we decided we want to use some specific GPU compute units to actually run our models on. But how do all of these things actually come together? So let's look at a potential high-level diagram of how these things can get assembled. So we begin with the sensors that we already talked about. So you have like LiDARs and cameras and so on that are kind of the inputs of the system. And it's very common in these kinds of robots to have some sort of cellular connection as well, because it's necessary, for GNSS corrections. If you're getting them in a cellular network, they might be necessary for dispatch, telemetry, remote assistance, over-the-air updates, map updates, whatever. So you need to make sure you have this enabled. Most sensors often communicate with some sort of central compute by Ethernet, although USB is also commonly used. It's a matter of just being consistent. And GNSS and other localization-specific systems often need to talk with some sort of positioning engine. And this can be a standalone computer, or it can just be your localizer software that's running on your stack. So for example, if you're using some sort of drop-in GNSS INS solution, your OxDS, Novotel, Planix, whatever unit, often this will be its own node, its own physical compute that you actually plug in the localization sensor into, and then it provides poses for your stack. But if you want to run your custom, maybe you're implementing a novel visual odometry system with event cameras or just your own LiDAR SLAM, then you'll probably want to run this on your central compute, and then you just wire everything to your central compute and do the processing there. And then typically you have the autonomy system that runs on this main computer, running your cool models, running inference, all this sort of stuff. And it produces either a motion plan or just directly the control outputs that are then passed to this high integrity compute that validates them. Maybe the high integrity compute itself is running the controller, and then this gets passed to the drive-by-wire system downstream. Okay, so now that we have kind of our conceptual setup, we know how we want to wire our computers, we know how to wire the sensors. How do we actually build this, and how do we integrate it with an existing vehicle, whether it's a small delivery drone or a truck that weighs 10 metric tons? So we begin with basically a design process for this engineering endeavor, and the output of the process is basically a detailed block diagram, which is much more detailed than just the system level diagram. And this is just one example of what this would look like. And often there's even more detail. This is just something from Google. So the process typically begins by reasoning about kind of what the requirements are on all of these sensors that we saw and where they should be placed on the vehicle. And this can be done heuristically, or you can actually use some sort of simulation to evaluate different sensor configuration and pick out the one you want. And then you build out the system block diagram based on these requirements. This is typically done by collaboration between software and hardware people. And this will cover basically what sensors and what modules you'll have on board, how they're actually wired together, et cetera. And then you kind of keep iterating on the requirements, gathering different requirements on vibration resistance, temperature ranges, and so on for all your sensors and all your computers, as well as requirements, even things like how fast the models need to run and how the GPUs need to be connected. And then you iterate on this and come up with the final kind of block diagram that you can make into a reality. And one interesting thing that needs to be stressed is that something that's often neglected in early prototypes is aesthetics, especially in first generation prototypes, but they are critical when it comes to kind of interfacing with OEMs and showing off your system. And they're also very important in aerodynamics because these heavy trucks with their big engines are very sensitive to drag. And furthermore, you want to make sure that all of these setups are not too heavy. And also down the line, they will be easy to productionize and kind of easy to add to existing vehicles. So this makes sure that things are easy to manufacture, easy to retrofit your vehicle, while also being aerodynamic and aesthetically pleasing. So the design process has some basic principles that you want to follow. So the most important thing is to not have to reinvent the wheel. So it's very important that if some off-the-shelf component exists and you want to move fast to build something, it's important to use it. And then once you make all these decisions, you have to follow the design process to actually put everything together into something that can be made in reality. So again, you start with building blocks that are these modules. So you have things like components, schematics, printed circuit board assemblies, various connectors and housings, and so on. The harness kind of tells you how these blocks communicate physically and logically. So actually how you physically wire a sensor to the computer is specified here. And sometimes it can be very challenging, especially if you have something as big as a truck. You might have an aftermarket wheel speed sensor and a GPS antenna, and they're like in different corners of the thing. So actually correctly and easily wiring everything up might be quite challenging. And then you need to consider, of course, the support structure of how you actually position these sensors. So these are the arms that support your LiDAR, various sensor brackets. These are very important because also they need to be resilient and not shift around when you're driving a lot to minimize the need to recalibrate the vehicle and make the job of online calibration easier. And of course, once all this is said and done, you need to use computer-aided engineering, CAE techniques, to actually make sure that the design that you put together is resilient enough. When you simulate it to thousands and thousands of hours of vibration, extreme braking, extreme wind, all that stuff. Okay, so let's wrap things up. So we hope that a key takeaway from this tutorial is that there's not one size fits all solution for autonomous driving sensors, compute, and mechanicals. And there's basically a ton of pros and cons that need to be taken into consideration when designing these things. So the key of robust and safe autonomous driving lies in being cognizant of these trade-offs and designing hardware and software solutions that basically leverage the strengths of all your different sensors while mitigating their shortcomings, as well as having plenty of redundancy amongst them. So thank you all for being here. Thanks for the attention. Thanks to the amazing hardware people at Waabi who helped contributing to these slides. We were going to have a 15-minute break, and we will continue with perception at, let's say, 10:30. Thank you very much.